We have two masses m1 and m2 that are kept on a rough surface and friction coefficient is given as k, and we have a spring that is connecting them, and this k dash we have assumed it's not given in the problem. We need to find the minimum force F, a constant minimum force F that we start applying on the first mass such that the second mass will move. So when we start applying the force on the first, so one thing is quite obvious, that this at least has to move. So that this spring will be stretched, and this spring should stretch enough to overcome this frictional force. And we need the force to be minimum. So you can just imagine that if we connect this to a wall instead of this block 2, and if we apply some constant force here, so it will go and it will stop after some time. So when it will stop, that time whatever is the stretch in this spring, that should be enough to overcome the frictional force. So again, assume that this 2, instead of 2 we have a wall here, so that it's easy to imagine that if you apply constant force, so it starts from rest and it eventually comes to rest. So now instead of wall we have a mass 2, but still the same situation applies. So when it eventually comes back to rest, that is the minimum force. Because of course if it has some more velocity when the spring is already stretched, then we are using excessive amount of force. And if it becomes 0 before that, it comes to rest before that, then the spring will not be stretched enough to move this block. So let's read that. For force to be minimum, block 1 will come to rest again when the spring gets the required extension to move block 2. So this is our condition. It has moved by distance x and then it has come to rest, and the force will be on the block 2 will then be k dash x, that should be equal to Fk. So let's write our equation on block 2, which is simply k dash x is equal to k m2g. Now from here to here it has gone from rest to rest, so we will do our energy conservation on on the whole system actually we can do. So this block is at rest, so on the rest of the system we will do energy conservation. So work external is equal to work done by friction plus change in potential energy of spring plus change in kinetic energy. So I have written here, I should write the magnitude, so there is no doubt. Otherwise what we are used to is work done by the external forces should be on the left. Anyway, so we can write like this also. So this is the energy lost in friction, this is the energy gained in our spring, and delta Ke is 0. So both the masses were at rest initially, and finally also both the masses are at rest. So work external because of the force F is Fx, and work done by friction is K m1g. Okay, there was some confusion, so let me just write it in its proper form of the equation. The total work external is equal to change in potential energy plus change in kinetic energy. Now work done by the force F is F into x. Work done by friction is negative because the displacement and friction are in opposite direction. So work done by friction is minus of k m1g into x is equal to potential energy of the spring half k dash into x square, and delta Ke is 0. So 1x will get cancelled and we are left with k dash x in both sides. So if we just replace the value of k dash x from here, so we'll get rid of both the variables k dash and x, and we'll get our answer, force is equal to k m1 plus m2 by 2 into g. So quite interestingly, the force is independent of the the spring constant. So it can be a thread or anything, the force is still going to be same, the minimum force needed to move the block.